Thank you very much for inviting me to present here. I'm going to talk about a couple of methods which have been already used for a while. In particular, statistical disclosure limitation methods, swapping and noise, which are among the most widely used approaches by statistical agencies for public use release in non-interactive setting, and when there is a preference to release non-synthetic data, when there is a preference to release some kind of perturbed version of the original data, but not the synthetic data. And the core ideas of these methods are actually very conceptually easy to understand and maybe to implement. So that's why maybe this is one of the reasons why they are so popular, at least among statistical agencies. I work for a statistical agency in US, and it seems that these ideas are naturally suited for masking, right? Like confusion of noise. This is how we understand masking or swapping some records. So I decided that they are worth revisiting them, but maybe with a special emphasis given to their utility aspects. So this presentation will be slightly leaning towards what Giuseppe said 2 days ago, utility first. It's not necessarily my position, but today I'm gonna utility, kind of leaning towards this, utility first. So I will describe how these methods can be combined together to increase each other's efficiency while protecting variables of different types. So just very quickly, noise is usually applied for continuous variables. It has desirable properties that it can preserve means in correlational structure in the data. Basically, if we add noise, which is normally distributed with a zero means and covariance matrix proportional to the covariance matrix of original data, maybe it will be equal to some constant C times covariance matrix of the original data. So, but noise, if added to the original values, of course, will not preserve some data-specific constraints such as positivity. Like in our surveys, we have a lot of positive or non-negative variables, like economic variables, demographic variables, and also inequality constraints. So basically, it would be nice to retain desirable properties of additive noise, but in addition to preserve these data-specific constraints. So one solution can be to actually apply multiplicative noise. This method actually recently gained some attention by some researchers, but mostly from the risk perspective. But the relationship between additive and the multiplicative noise is simple. If we transform original data to the log scale, then we add noise, maybe normal noise, to the log transform data, and then we do the back transformation by exponentiation when we get original data multiplied by exponent of noise. So by analogy with additive noise, we can actually require that desirable properties of additive noise would be satisfied for multiplicative noise. Okay, and we're not going to release just original data times noise or continuous original variables times noise, but we're going to release the transformation, which is given by expression 3 here. And it's actually straightforward to verify if the requirements which we decided to impose are satisfied, given by 2, then such a masked data will be positive and will have the same means and the same covariance matrix. So the good thing about that is that constant C, which is a parameter of noise, doesn't need to be released for variance inflation adjustment. But by the way, agencies, as far as I know, don't release it anyway, even if it's additive noise. But more importantly, there are actually indications from the ongoing research that release of this parameter C for multiplicative noise can be dangerous from the disclosure perspective, because it can lead to attribute disclosure, because multiplicative noise is quite correlated with the original values. But in this case, we don't need to release it. Okay? So, and the last thing that I want to add here is that what kind of noise would satisfy these conditions. So if we choose the distribution to be normal for the noise which is added to the log transform data, then it's possible to verify that the solution of this system of equation is given by expressions 5. So this is a normal noise with such a mean and such a covariance matrix. This is the ij element of the covariance matrix. So this noise actually has a particularity that it will lead to the log normal distribution exponent of noise with the shape which is quite similar to normal. So if you look at this picture here, so the red curve shows the normal density, and the black one is just a kind of typical noise with such a parameters. So the introduced skewness in the mask data in this case would be minimal. Okay, and I have a couple of slides for the general case when we have different types of variables, when we not only have non-negative variables, but also we have variables which can take negative and positive values, and also variables which obey inequality constraints in our data, and we want to apply this multivariate multiplicative noise which will preserve the moments and these constraints. So then we will need a slightly different transformation, but unfortunately I don't think I have much time, so I'm going to skip it, but the basis is still the same. So I'm going to skip the slides and I'm going to go to the second part. This is about swapping. Again, swapping is one of the oldest, if not the oldest, methods of disclosure limitation. And I've seen this mostly applied to categorical variables. In principle, it can be applied to continuous too, but at least I haven't seen that. And the problem with swapping is that it can negatively affect the relationships between the variables. And especially it can be problematic when these variables are the design variables or the strata-defining variables or variables defining important subgroups in the population. So I'm going to present an approach which is similar to swapping, but which takes into account relationship between the variables. And I will show how these two methods, this version of multiplicative noise and swapping, can be used together so that the relationship between swapped categorical variables and continuous masked variables would be preserved. So the version of swapping, well, I call it conditional group swapping approach, or CGS, maybe abbreviated. It's basically it is designed for to mask strata-defining variables when we decide that we need to mask strata-defining variables. For example, it can be area of residence, right? If we stratify by area of residence, well, assume there is a high-income area of residence near Washington, D.C. in U.S., Chevy Chase. And like I work in the area where it's much low income, Hyattsville. So if we choose randomly two individuals and swap their area of residence, it can happen that individual maybe with no income would be moved or swapped with somebody who is very rich and live in Chevy Chase. And this will introduce inconsistencies in those strata, so we don't want this to happen. So this method or this kind of approach will try to minimize this. And how we do that is that first we move or we swap the records between the closest strata from the point of distribution of the strata, and I use probability proportional sampling to choose the records that should be moved from one strata to another. So the probability of selection of the record to be moved to another strata or swapped will be proportional to the probability of classification of this record to the stratum where it's being moved. So I'm trying to choose the best records or give the preference to the records which fit better that strata. I don't want to move the extremely wealthy individual to the area maybe which are on government assistance. Okay. So, and here is I'm going to just outline the main steps of the algorithm. So, first of all, again, we have the stratified data. We can compute pairwise distances between the strata. We can use different metrics of distance. Well, I use the propensity score distance, but This propensity score metric was actually proposed as a measure of utility, but in essence it's just trying to assess discrepancies between the distribution of masculine and regional data. So why not to use to measure relative distances? We can do it as well, because it gives us just one number, right? We can get the pairs of closest strata. So then for the records in, let's say, two closest strata, A and B, we're going to compute swapping probabilities in the following way. So for every record I in stratum A, we will compute conditional probability that this record is assigned to stratum B, although it's from A, but we'll compute the probability that it belongs to B, given the values of the variables for this record. So basically we will compute this propensity score. And next, we're going to select some number of records, which is a predefined swapping rate, and we're going to select these records with the probabilities proportional to their propensity scores, and we're going to change the stratum indicator to B. And then we'll do the same thing for the records from B, so we're going to compute their propensity scores, right? And we're going to change their, select these records and change their stratum indicators. And we're going to do this for another pair of strata until there is no more strata left which have not been swapped. Okay? So we're trying again to minimize the impact of swapping by taking into account, the values of other variables. And how can we combine swapping and noise, at least that variant of noise and this variant of swapping? So again, this is can be applicable for the stratified data. So after we compute pairwise distances between the strata, what we can do, for the closest strata, we can estimate model parameters to compute propensity scores, but we're going to do it based on the regional data. This is the model, right, to compute propensity scores. And here V1 original, V2 original will be variables or their functions of the regional data. But we're not going to yet compute the propensity scores themselves. We're just going to estimate this model. So we are learning a rule, classification rule, based on the regional data to do the swapping. And then we're going to apply multiplicative noise for the continuous variables in strata A and B. And then we're going to compute actually these propensity scores. But we're going to compute them using this model, but we're going to plug here the masked values for the appropriate terms. So the model, right, classification model is learned on the regional data because we want to preserve a regional relationship, but masked values, right, are taken into account. So actually I noticed that when I did this for the data set, in some cases when maybe rare cases when a big value of noise was generated for some particular record, and it happened sometimes that this record now was kind of not very representative of that strata, but was maybe more representative of the strata B, right, which was swapped. So propensity score increased considerably for this record, and it was moved to the stratum B. So basically, kind of in some sense, swapping slightly can correct the inconsistencies created by noise, right, in some cases. So, here are the results of numerical experiments. I try to be quick. Well, I apologize, I didn't use one of our real surveys because the process of obtaining approvals for present the results or publish, it's very lengthy, like 5, I think, steps. I didn't have so much time, so I just downloaded a while ago actually a data set from the website Kaggle. It was a public data set, Titanic. So this is just historical, this is the records of the 889 passengers who traveled with Titanic and British passenger liner, which sank in Atlantic Ocean on 15th of April 1912. And there are, at least in that data set, there are 8 variables: survival status, yes or no, passenger class, first, second, third, sex, age, number of siblings or spouses aboard, and so on. Before applying these combinations to the Titanic data, I think it's actually always useful to think hard or to dig into the area. So what are the possible uses, right, for this data? And for Titanic data, actually one of the possible analysis would be to figure out what sorts of people were likely to survive in Titanic sinking. And in fact, since this disaster, there was a very kind of widespread belief that that the social norm, women and children first, gives survival advantage to women over men, and then that the crew members actually give priority to the passengers. But recently, well, relatively recently, I saw an interesting study by Ellender and Erickson, which was basically presenting historical records over 300 years, and it was completely different picture. Like actually, they showed that women die at significantly higher rate in maritime disasters, and actually the highest survival rate was for the crew members. So it's more like everybody for themselves instead of women and children first. So according to Ellender and Erickson, events on Titanic where 20% of men, only 20% of men survived and 70% of women survived, were highly unusual, if not unique, and can be attributed actually to the direct orders of captain of Titanic, who ordered to save women and children, but of course according to the class. So basically, based on these considerations, I decided to divide the data set in 6 strata: first class male, first class female, second class male, second class female, and so on. And goals of the numerical experiments were to see what are the potential benefits of using conditional swapping probabilities for data utility, and to test the combination of multiplicative noise and swapping. How well does it work? I used a couple of measures of data utility, analysis specific. I compared confidence intervals for the regression coefficients for some regression. One regression was survival status, regressed on class, sex, and age, fit to the complete data, and another was a logistic regression survived on age and fear, fit within each strata. And as a measure, I use a relative overlap of confidence intervals given by expression 10. Right? It's basically just it will be equal to 1 if they coincide, original interval, mask interval, 0 if they don't, and will be negative value if they are at some distance. This value would be increasing. Okay, and here is the results. So these 3 columns is this conditional group swapping, and here is basically very similar approach, but the probabilities of swapping were computed as uniform. So records are swapped between exactly the same strata in the same order. It's just the strata we choose in the same order, but they're uniform. And if we can see the average overlap over all coefficients and all realizations, I generated 100 realizations, were quite higher for conditional group swapping than for the case when probabilities were uniform. Okay, and I'm trying to kind of wrap it up. I also use the generic utility measure, propensity score, based on propensity score, and here if we see the smaller values means better utility, so it check general discrepancies. So for conditional group swapping it was much higher values than for random, so here differences are more pronounced. And here are the results for the combination for regression specific utility. So this is the combination which I just described. So the model for propensity scores were estimated on original data, but propensity scores computed on the mask data. And here a slightly different combination, just for comparison. So I applied swapping to the original data, and then independently within each swap stratum I applied noise. Okay, so first of all we can see that these values, average utility here, are almost the same as for swapping alone. So it seems like noise doesn't actually contribute to the utility loss, to the utility loss at all, but which is not surprising because this noise preserves the first two moments, which is necessary for regression, so I mean, kind of is perfect. The comparison between the methods which are basically dependent one on each other and, well, slightly independent, well, I don't know if it's, we can say like that. Well, there is a slight improvement here, but not too big. And I assume that this is because, again, multiplicative noise preserves these first two moments, and even if they are not so much in, you know, in a not so much dependent as in this combination, but still, you know, it gives a good results. But if instead of this multiplicative noise I use something much more perturbing, I assume that I will see like bigger differences, but I haven't tried yet. And here are the results for generic propensity score utility. So I want to I go to the conclusions, right? Because I have like a minute, right? 2 minutes? Well, I'll do. So, well, multiplicative noise scheme seems to be a good choice for masking for continuous variables that obey sign constraints and inequality constraints, and for the analysis when we need to preserve the first two moments. This conditional group swapping also may be a good choice for the stratified data when we need to perturb strata-defining variables, and it's important to preserve at least to some extent the relationship between the variables. And it seems that combining multiplicative noise and swapping, this type of swapping, has a potential to improve distributional characteristics of the data when the methods are applied sequentially and conditionally on each other. And like just a few words about the risk. We just carried out an initial risk assessment for this combination. So we computed re-identification disclosure risk, which is defined as an average percentage of correctly linked records when record linkage techniques were used to match original and mask data. So it's just an empirical estimation of risk to have an idea. So for Titanic data, the risk was quite low, with about 4% of records were correctly identified. Although, as the you know, like many presentations before, they showed that there are very many aspects of risk that we have to take into account, and the thorough investigation of disclosure risk for these combinations and others is a topic of future research. So thank you very much. That's it.
More time for questions and discussions, so well done. Questions? Ed?
Yeah, so the conditional component of the model. So I'm curious about this. So the random component in the original model kind of prevents reverse engineering of the strategy and what was the underlying data. Does the conditional
Is this also random? Because it's just the records are selected randomly. It's just not the probability of selection is not uniform. It depends on the. So it's still, even with somebody would be maybe, you know, not extremely well fitted for the strata where we are trying to move it. It still there is a chance that it will be swapped. Yeah. So it's still random. It's just not uniform.
So the ONS did record swapping in the last census, probability proportional to size, on whether it was high risk or not. So we can also playing with that as well.
Yeah, this can be.
In this initial risk estimate that you derived, is there any difference between using just swapping or combining with multiplicative noise? Is the risk the same? Whatever the method you use, or does
this is actually just the risk for that particular combination that I computed just to have an idea. But yeah, other methods I assume would be maybe different.
Can you say a little bit more about how you preserve edit constraints? You know, because when you add additive noise, and the covariance matrix is, you know, based on the original mean and variance, and you just add noise and additive noise, then you preserve the sufficient statistics, but you also preserve these edit constraints like, you know, revenue plus profits is equal to turnover, that sort of thing. So how does your method sort of deal with these types of edit constraints? You did mention that.
Well, I mentioned only that it actually exactly preserves positivity and inequality constraints. So maybe, I mean, I have to look into whether this, this functional constraints will be preserved, or maybe it requires some other modification. But maybe it's actually, it will be quite easy to do this if we do the synthetic data, because we can all put this in the model. But because I said that I try to look into the, perturbative approach, there it's harder because you don't have so much, degrees of freedom to generate. But I will look into this.
Obviously, you can only apply the multiplicative noise for variables that are strictly positive. But you get a lot of data in the real world where it's positive but with a number of zeros. Can you cope with that?
For non-negative values, yes, we can do. And there is an extension here which, when some variables are positive and negative, and other variables are non-negative. It's still, but it will be slightly different transformation. We need to do a few more steps before we get to applying that noise, because sometimes it can happen that you can't compute the covariance matrix in the case when we have positive and negative variables. And but I'm assuming that zeros will stay zeros, because when you multiply.
Yeah, obviously.
So this may be risky. So, but I have to look.
You find them as a separate category, and then, which quite often is a good idea.
We'll think about.
One final question. Okay, thank you very much.
Thank you.